Hello everyone and welcome to today's video where we're walking through question 21. X1, X2, X100 is a random sample from a Bernoulli distribution with probability of success Q. You perform the hypothesis tests. H null is Q equals 0.5 versus alternative hypothesis H sub 1 is Q is greater than 0.5. The critical region is chosen to be C equals the summation of x sub I from 1 to 100 is greater than or equal to 60. Calculate the probability of a type 1 error. For this problem, the first thing you need to know is what type 1 error is, and that is the probability that you reject the null hypothesis, given that the null hypothesis is actually true. The second thing you need to know is the central limit theorem, and that's because we're going to do an approximation of this test using the central limit theorem. So to state that explicitly, suppose x sub 1 to x sub n is a sequence of independent and identically distributed random variables with the expected value of x sub I equal to mu, and the variance of x sub I equal to sigma squared, where sigma squared is less than infinity. Then, as n approaches infinity, the random variable square root of n parentheses x bar minus mu converges in distribution to a normal 0 sigma squared. As an illustration of this, I just created a simulation of an absolutely ridiculous PDF. So a fourth of the time it's uniform from 0 to 1, a fourth of the time it's normal with mean 20 and some variance, or normal with mean 50 or normal with mean 80. So just a really complicated distribution here. But if you were to randomly sample 100 samples from this distribution and take the mean, and then you were to randomly sample a separate 100 observations from this distribution and take the mean, and repeat that 10,000 times, what would the distribution of those sample averages be? And here we see that even though we have that absolutely ridiculous looking distribution, the sample average from that distribution of size 100 follows a nice normal curve as shown here, approximately. And the central limit theorem is just saying that instead of a sample size of 100, if you had an infinite sample size, it would be perfectly normally distributed. So that's just visually what's going on with the CLT. So just as sample increases, it more and more closely aligns with a normal distribution. And we can use that to approximate these probabilities. So again, going up to the question, we're going to use the normal curve as an approximation, but really if we wanted to, we could get the exact probability of every event occurring, right? Because we could say, how many ways can we get 0? Well, that's the probability 0.5 to the power of 100, and there's only one way that could happen. And then what's the probability of one of the x's being a success? Well, that would be 0.5 to the power of 1 times 1 minus 0.5 to the power of 99, and then there's 100 different ways of ordering that. And we could do this for all different possible values of the summation of xi and get an exact probability. But as you imagine, that's quite computationally expensive, and we're just going to do a normal approximation. So that's just, again, talking through CLT, so now to actually jump into the calculations themselves. First off, we have our null hypothesis is that the success rate of these samples are 0.5, and then to apply the CLT, we're going to take the variance of a Bernoulli, and that's just p times 1 minus p, divided by the sample size, in this case 100, and then take the square root of that. So 0.5 times 0.5, the square root is just 0.5, square root of 100 is just 10, and then we get sigma is 0.05. Next we want to know, okay, we have this critical region in the problem defined as greater than or equal to 60. Well, if we want to convert that to a sample average, that's just equivalent to having a sample average of 0.6. And then what we can do is say, okay, well, if we have a mean of 0.5 and a standard deviation of 0.05, how many standard deviations away is 0.6? So that way we can get it to a normal 0, 1 curve and use our z table. So here is just solving for z, and we see that z is 2 standard deviations. So to express this visually, using our CLT, our normal approximation of the sample average of these Bernoulli trials, it would be mean 0.5, standard deviation 0.05, and our critical region starts at 0.6 and goes to the right. Now the purpose of this question is to solve for the area under the curve, this blue area. And so when we convert this to be a normal 0, 1, we see that it's just 2 standard deviations away. And at this point we can move to our z table. So this is one I found online. I think when you actually use the z table on the exam, it's positive z values. So you're going to see values like 0.9997 instead of this 0.0003. So you would have to do 1 minus these values. But going to negative 0.2, since the normal curve is symmetric, the area to the left of negative 0.2 is 0.0228, which means the area to the right of 2 is that same value. And that is our answer. So the probability you reject that the true sample success rate is 0.5, given that the success rate really is 0.5, is 0.0228 using this normal approximation. At this point, I do want to mention the continuity correction. So if you were to refer to Mahler's solution manual, he actually gets a different answer. They both result in the final answer being C. So just want to walk through first the simplest form, which is what I just did, but there's actually a better answer, and this is the one you should be using for this question. They just luckily worked out to be the same. And that is, in our sample size of 100, what are the possible values of our sample average? So since we have 100, we might get 50 successes, and that corresponds to a sample average of 0.5. Or if we got one more success, that would be 51, 52, 53, so on and so forth. So you'll notice that there's literally only 101 possible sample average values ranging from 0 to 100. That is even possible. And so when we say what is the area to the right of greater than or equal to 0.6, when we express that in terms of our sample size, that should be equivalent to less than or equal to 1 minus less than or equal to 0.59, right? Because you can't have 59.5 successes in our sampling. And so we definitely know the area to the left of 0.59 is one thing, and the area to the right of 0.6 is another. But the area between those two values is ambiguous. How should this be assigned? So in the solution we just did, we chose to assign this completely to the red area and say we're only concerned with greater than or equal to 0.6. However, it's better to say, okay, well, this orange region doesn't really directly correspond to one or the other. So what you can do is just split the difference and say, okay, instead of considering 0.6 for our critical region, we're actually going to use 0.595. So that way, half the, not half the area, but half the distance between those two values. The area to the right is assigned to the blue region, the area to the left is assigned to the red region. And so if you do that instead, and if you prefer to just read the reasoning, I also have this in text form, but if you use this value instead of 0.595, you actually get a z-score of 1.9. And so going up to our table, instead of going to this -2, you would go to -1.9 and get 0.0287. And again, in both cases, this results in the same answer of C. So at this point, I would say, for this problem, if this were on the exam, I feel like personally I would want to contest this if those two answers weren't aligned. Let's say one was B and one was C. I would personally contest this problem if I answered in either case, just because the question doesn't explicitly tell you to do that continuity correction or not. So that's just my opinion. I don't know if that would actually hold up. I would say that it is better to do the continuity correction than to not. So if you get a repeat of this question on the exam, I'd recommend to do the continuity correction. But I do feel like this question's a bit ambiguous and would prefer that they explicitly say to apply that continuity correction. But that being said, thank you for watching. Final answer for this question is C in either case. And if you find these videos helpful, please consider subscribing. Thanks.